In this video, we'll look at transformations of functions, horizontal stretching and shrinking. So previously, we've talked about vertical stretching and shrinking, that is, when we take some constant, we multiply the output of a function, which has the visual effect of stretching a graph vertically or shrinking it down towards the x-axis. So the question here is, what will happen when we modify not the output, but the input? So we say, what if we have a y equals f of cx, or like y equals f of 2x, 1/2 x. Point being is that we're modifying the x, we're not modifying the f in this case. So to begin, let's consider when we have f of x equals x squared. We know that this is one of my favorite graphs to work with. It's an easy one to graph, and it's an easy one to see what everything looks like once we've modified it. So we know that this looks something like that. At -1 and 1, the graph takes on the value of 1. At -2 and 2, the graph takes on the value of 4, so on and so forth. So what I want to find out is what's going to happen if we graph f of 1/2 x equals y. That is to say that we're plugging in 1/2 x in for our variable in the first equation here. So we can kind of think of this as 1/2 x quantity squared. So let's plot some points and consider what's going on. So if we plug in 1 for x in our new f, we have f of 1/2 times 1 equals y. So that would be 1/2 times 1 quantity squared, which would be a fourth. So at x equals 1, we have a fourth. So then at 2, we've got 1/2 times 2, which is 1, quantity squared, which is 1. And then we go on, same thing on the negative side of the axes. And we can see that it's going to look something like this. So when we graph 1/2 times the variable, the input, the way we can think about this is we're changing the rate at which this graph will grow. So it's going to take twice as many units in the x direction to go the same amount in the y direction. That is, from 0 to 1 on f of x equals x squared, we have like an average rate of change of 1. And going from 0 to 2, or 0 to 1 on 1/2 x quantity squared, we have a quarter slower of an average rate of change. So it changes dramatically the rate at which the graph grows. Another example to consider, when the constant modifying the variable is not less than 1, right? This first example we considered when we have 1/2 x. What happens when we graph y equals 2x quantity squared? So you might have an idea with this based on this first discussion. When the constant modifying the variable is bigger than 1, the y value, the height of the graph, will change much faster. And we can prove that to ourselves real quick. When we plug in 1 into y equals 2x quantity squared, we get out 4, because we have 2 times 1, which is 2, times itself squared, which is 4. And then if we do 2, we have 2 times 2, which is 4, squared, which is 16. So this graph, it will grow extremely quickly. It will look something like this. Like that. So it hits the same y value as the base graph in much less time. So we can kind of see that if we have a constant modifying the variable where the constant is less than 1, between 0 and 1, then it'll expand, it'll stretch horizontally. And if we have a constant modifying the variable that's greater than 1, it'll shrink the graph towards the y-axis. And we can do this with all kinds of graphs. So we've got some graph of y equals f of x below. It's this kind of zigzaggy, sawtooth looking graph that continues in this pattern in the negative infinity direction and the positive infinity direction. If I wanted to graph y equals f of 2x, what will happen? Remember, just like before, if the constant modifying the variable inside the function is greater than 1, then it'll shrink the graph towards the y-axis. So we could redraw this like this. So now the graph is repeating itself twice as frequently in the same length of time as the original graph. So we will have something that looks like this. And you kind of get the idea here. We could go on. Just important to note that when c is greater than 1, it compresses the graph, shrinks it towards the y-axis, and when c is between 0 and 1, it stretches it away from the y-axis. So, in summary, horizontal stretching and shrinking of graphs. To graph y equals f of c times x, so if c is greater than 1, you'll shrink the graph of y equals f of x horizontally by a factor of 1 over c. If c is between 0 and 1, you'll stretch the graph of y equals f of x horizontally by a factor of 1 over c. I think the 1 over c notation can be a little confusing, but just remember that depending on the size of c, it'll either take more units of x or fewer units of x to achieve the same, quote, x value as our original function f of x. So you can see in these two images below here. So y equals f of c times x. For c greater than 1, again, shrinks. And then y equals f of c times x for c between 0 and 1, stretches it horizontally along the x-axis.